Don't worry about Jeffrey Hinton, all that. We're still stuck in the 40s and 50s with the perceptron, right? But already in 1957, they made this connection. Where in that curve, we need to go down. Oh, sorry. I need the whiteboard. Okay, so we're still in 1957. We've established that um, we have, a chart like this. We have the error over here. We have W over here. We know that the error function is a relationship of y minus y hat square. We've established that. That has a shape that looks like that. Widrow and his student, Ted Hoff, they're here and they're like, okay, in this graph, I know I want to go down because I'm trying to minimize the error. If I am here, I want to go that way because I want to minimize error. So they understand that and they start searching and they figure out that calculus says that if I have a curve sort of like that and I have a point in it, if I perform this operation called a derivative, I can get this tangent value, but that can be used to determine then which way to go down. Got it? All right, so now let's derive it then. So to derive this, I'm going to derive, remember, the perceptron rule, which is very interesting. So we need to have an equation, right? So in this case, our equation will be the x0, w0 plus x1, w1 plus b. This is the equation, let's say, that we are trying to figure out, right? So we're trying to figure out this equation. So we know that the error is actually going to be y minus y hat square. Okay, so then, okay, he says, all right, let's apply this technique from mathematics, right, to get that value. So he does the derivative of the error, I'm just going to use E, in terms of one of the weights. So in this case, what you care about, remember, is the weights, right? Because that's what you're moving for. So we're going to say that the partial derivative of E in terms of W0. He applies that derivation. So now let's write it out. So that should be so this is written. So the function is written like this. Okay, this may be hard to understand, but this is how this is written. So it's gonna be 2. You make it negative, then the 2 just comes down. So it's like the 2 becomes a value here. You still have your y minus y hat. Y hat no longer squared. And then you take the partial derivative of y hat in terms of W0. Okay? That's how it's written. This is just like Isaac Newton came up with this math rule. Okay? That's all you need to, it's very mechanical. All right, so then you rewrite this as minus 2 y minus y hat. And now it's going to be the derivative of just the y hat parameter. So that's x0, w0 plus x1 w1 plus b in terms only of w0. So essentially all the parameters become constants, and when you derive a constant, it becomes 0. So it just goes away. So then the answer to this is -2 y minus y hat, and this term here becomes just x0. You see that? Everything is a constant, so the only thing that is in terms of w0 is this parameter. So that w0 goes away, and you just get x0 as the answer. Again, just a mechanical calculus operation, okay? But so you discovered, you'll see that there's something very interesting going on. You get for the derivative of error in terms of w0, this x0. Notice that this w0 gave you x0 there, okay? Very important. Then you do the same for the other ones. So I won't write out the other ones, but they're essentially the same. So when you do the derivative of E in terms, now see, initially we did it in terms of W1, right? You guys get that? Oh, sorry, of W0. Now I'm going to do it in terms of W1. The answer to this one is -2 y minus y hat. This is now a constant, and now you're going to derive in terms of W1. So the answer would be x1. You guys see that? That's x1. Make sense? So you're taking the derivative of the error in terms of that weight parameter so that you can figure out how to update that one weight parameter. So you know here, this is the information that you need to know which direction to go in, because that's what this is going to give you. So this one, for W0, it's in terms of X0. For W1 is in terms of X1. And you can start to see a pattern that for every W3, it would be X3. For W5, it would be X5. And now you can see it's starting to look a lot like the perceptron update rule. So that's essentially the intuition. Just for completion, B, when you do it in terms of B, there's nothing there, right? So it just becomes 1. So then the WE in terms of B is just going to be -2 y minus y hat. No parameter. That's it. So you had a function, you knew that you wanted to calculate that slope. If you took the derivative of that function in terms of the parameter that you were trying to determine, it gives you the actual modified equation that you can use to compute if you should go up or down. That's just how it works. It's math. And so if we generalize this equation, then I can say that the derivative of E in terms of Wi, right? So Wi is going to be equal to -2 y minus y hat xy. Xi. So it's always that. That's the perceptron rule that you saw in the code that I gave you guys. So now you have this parameter here. And so that's how this parameter gives. So in conclusion, what does that parameter give you? Remember? It gives you the information that you need whenever you have the function This is the function. You take the derivative of it in terms of this parameter at this point in time. Doing that is going to give you a new formula that will tell you if you should add or subtract, because it tells you if you should go up or down. That's it. And that's the derivative of the perceptron rule. So let's see if I'm telling you the truth. Okay, I'm going to go over here. I did it for W0 and it looks like this. I did it for W1, it looks like this. This is the bias. I generalize it so that any W is just Y minus Y hat Xi. The two really doesn't matter, right? And then all you need is the learning rate. So there's three things. Y minus Y hat, the actual Xi that corresponds to that W, and the learning rate. So that's the derivation of it. So let's take a look now at, I need to share the screen probably for this. So let me, so now I'm going to share the screen. We're going to go back to the Python code. Okay. So this was the Python code. So that equation is what I just derived. So if you look, update is equal to the learning rate times ypred minus yreal. Notice it's not squared. And the formulas that I derived are not squared. And then that update is multiplied times xi. Do you see that? Where xi corresponds to the particular value. So if it's W0 that I'm updating, then it's X0. If it's W1, it's X1. If it's W2, it's X2, and so on. And that's where it comes from. Here, actually, weights are a vector of 2, and Xi is a vector of 2, but they correspond. So, and notice that for the bias is update without any parameter. So it's exactly the same. Do you guys understand? So let me, that's the equation there. If I go back to the whiteboard, in Python or in the Anaconda, the update rule is like that. It's a vector where this is 0 and this is 1, right? So it's a vector of 2. Plus or minus learning rate y minus y hat times x. But x, so y hat, and this x is also a vector of 2. So essentially you're modifying, another way of saying it is if it's this wi is equal to wi minus or plus learning rate y minus y hat times xi. So they actually, this was the perceptron learning rule, but it comes from that derivation. So this would give you essentially the parameters, and that's why it works. All right. So that's it. That's the derivation of where you get the learning rule for the perceptron. And just keep in mind that applies also to all the other neural networks. They just get a little bit more complicated in the function, etc. But that's it. This is the perceptron update rule right there. Okay. All right. So we'll stop here for today. So that